going to present to a work about face technology regarding synthesis. So very briefly, well, these are 4 points. I introduce the task and a previous work, which is not going to be presented extensive, just some key points we need, and well, I presented the method and some experiments, and we close this talk. All right, well, just very briefly, the face synthesis detection is a task to determine where a face has been artificially generated. So this is a binary classification problem to solve. So, well, this face you're seeing actually is it's a fake one. So, well, in deepfakes, we use these methods to detect if some content that has been artificially generated. So it's part of the deepfakes technology detection as well. So it's very important to detect if the face is synthetic or not. So, well, what is the motivation for this synthesis detection? So, well, as it is, current methods achieve very competitive performance. Well, that's a fact. There is an issue. The existing methods offer no protection against well-known machine learning attacks. So that's what we see on the experiments section. So there is a mention about the vulnerabilities of using third-party models of data. So this is important because we found something in this area. So so we start with the previous work we've been doing on this year. So we have what we tried on the last quarter is to gain control of the synthesis. I mean, as it is now, you generate a bunch of faces, but you really don't have control of the process. I mean, you just generate and see random faces, but imagine that you want to generate a face with specific attributes like a female or children or elders. So we want to have control of the synthesis process. So we investigating if that's how good we perform on this task. So if we inspect the latent space, Santosh mentioned before, we have some elementary information of this, and we can start from this. So you see this plot after the dimensionality reduction. So you see that some areas in the top corresponds to people from Asian background. So in the bottom part of the plot, you see that's more Caucasian people. So you see that there are differences, and we can learn from this space. So, well, here it's more evident, right? So on the right side of the plot, we see the females. On the left side, we see the males. It is exactly the same plot for the three subplots. Difference is that we only assign different colors for the labels. So we actually label the data set. So it was a lot of work, but we were able to see the differences. So in the middle, for instance, there are children. So it's more difficult to distinguish if it's a male or a female, depending on the age, right? So when they are very young, they look similar, right? So it's very difficult to distinguish. So in the middle plot, we see that ethnicities like Latin, Caucasian, Asian, and African. So you can also see the differences between specific human traits, right? So on the right side, we see the age of the person. So young as they try to concentrate in the middle, and as people grow old, they are in the other part of the plot. So there are differences, and we can learn from this. So this is what happened when we actually use this information to synthesize faces. So the first row is Asian males. So the middle row, there are young Latin and Caucasian females. And well, we have the all Caucasian females on the last row. So actually the synthesizers learn this information, and we can pass the semantic information to generate the faces according to one specific profile that we need. So that's the previous work. So now what we're working on is, okay, let's detect how good we are detecting the synthesis. So this is what we propose. So we can seal the architecture and protect the model before making predictions. We will see the importance of this, of not disclosing the architecture, and also it is very important that we take the decision based off of the model confidence, as we'll see later. So what is the method? We have a real synthetic phase on the training set, and we'll start training from there. And we have model banks. So this is basically a collection of models. right now is just different architectures of models. It's a standard models from CNNs. So then we proceed to protect the the, the, the predictions, right? Because this stage is where we don't directly make the predictions for the next stage. We'll see that if you directly pass from the prediction to the decisions, I mean, there is no protection as it is now. I mean, anyone can take a prediction and start seeing what it actually is making the model to decide, and this is where this is not very safe to perform this stage. So what we do is to take the last layers of the models and protect those layers and produce a new feature space which is protected, and then retrain the feature space with a new model, which is the Bayesian model. And at the end of that, you will take the decision whether the input sample is real or fake. So it's a cascade to protect actually the prediction. So, well, it has here a Bayesian model, I will talk later, and well, at the end we have only the decision, which is based on some decision boundaries. So, well, the model bank is just, we have K models, right? And we pass the input sample. And well, this is only the last, we use the last layers, I mean, the decision layers before entering into the fusion model. So the latent space is just what it comes out from the convolutional field. So this is a very straightforward formulation from the CNNs. So this is where we protect the model. So we have the design matrix, which is produced by the model banks. So we have our samples, and each sample is to be mapped by the function. We have this function, and this function is taking the decision layers from each of the individual models, and they produce a new feature space. So we randomly generated the coefficients and the exponents, and all of them, they belong to the integer domain. So this is very convenient because we don't perform quantization for this to create this new mapping, and at the same time, because we are randomly generating this polynomial, we can keep those coefficients and use them as a key. So we actually protecting the model because we only have that key. And actually, we are creating a new feature space with the attacker to Signar. So he needs the key, or well, the attacker needs the key to make new predictions. So that's what we actually in this stage we are protecting the model against someone which is only forcefully require the key to make new predictions. So we have to protect 2 times Q integers per fusion model because we are using the last 2 layers of the decision models individually. So later on, we use a Bayesian model. So we have the target variable, which is actually the true labels, and we have our vectors, right, which is what is coming out of the polynomial fusion. And we need to estimate the parameters or a neural network model. We use a Bayesian model because instead of using weights, what we have to learn is the means and the standard deviation of each individual connection. So this is very convenient because those models are less prone to overfit. So I mean, you calculate over and over the mean, and you calculate over and over the standard deviation. I mean, you're wasting computing processing, right? But it's not going to be overfit as easy as you computing and dissipate the loss of the weights. So, well, there is some work existing on this, that these models are better in that situation, that overfitting is less likely to happen. So we estimate those parameters, which is basically featuring calculating the means and the standard deviation of the model. So, well, there's not many technicalities on this, but well, we check how it performs. So basically, we want to see well, this, for instance, the first one is wrongly classified, right? So you have the green label is a good classification. So the model performs very well, and this is what happens when we try the different splits and different synthesizers. So we have a regular existing model like ResNet and This is one we propose, the green one. So, well, I'm not presenting the model because it's a bit extensive, but we also have standard models like the SNet and visual transformer. So in the right side, what we have is that we vary the number of samples we use into training. So if we are to the left side, we're using about 10% of the data for training and 90% of the data to predict. So the performance should expect to be lower. And on the right side, we also where we are almost using all the training sets for training and, well, just 10% of the data just to make predictions. So on the right side, we see that depending on the synthesizer, we have different results, but most of them, the accuracy is very good. And actually, this is what it's already reported. So the accuracy detecting this synthesis is very good for most of the models. So we are on the same scale with them. So these are the results for the accuracy for different synthesizer and split values. What we can see here is particular when split is like about 10, 20, and 30%, which is the first. We have good accuracy actually, and this is from the very beginning. So this is very good because well, it means that we need not that many samples to train and have good accuracy making the predictions. So this is a good contribution because it means that the Bayesian fusion requires fewer samples than, well, the compared models. So this is a very good outcome of this work. So protecting the fusion, we randomly initialize the training set so to evaluate the confidence intervals. So we also record the number of times the model needs to retrain. So this is what happens. We did it several times, and we will see that most of the time the error goes down, right, the loss. And at the same time, a model becomes more confident in making predictions. So this is the way it works. So we have a small error. It's because we have our model is making predictions. We're more confident. So it's the way it works. So on the right side, we have the size of the key we use to fuse the model. So we have different sizes, right? And we test two cases when we have medium-sized keys and we have very long keys. And what we see is that on the vertical axis, we have the number of times we need to retrain the model because it doesn't converge very fast, or it takes a lot of time. That's because we are projecting the data into a new space, and that new space is very difficult to fit. So that happens when the key is very long. So I mean, we are going to protect the model better. We need a longer key, right? But also it means that the model maybe not converged, and we won't be able to train the model good. So what we found is that medium-sized keys are still protecting the model, right? And I mean, the accuracy is still good. So it means that we cannot use that very long key, so we have to use medium-sized keys to protect the fusion model. So that's what the experiment reveals. And well, and then we proceed to perform some standard attacks. So we'll evaluate how this fusion model performs when we attack the model. So we have 4 cases. We test for very common cases. The first case is the pollution attack, which means you only change the labels from fake to real, or the way around, in order to make the system fail. So of course, there's 2 ways to do this. You can form spear attack, which means you either pollute fake samples or real samples. But we did it both, right? Because it would be a lot of experimentation. So we basically pollute both classes, right? And this is doing with the pollution attack. And the next one is the perturbation attack, which means you only add a small modification to the samples in order to make the system to fail. So it's exactly the same sample. You only modify a little bit. In this case, you will see figure number B is we add RGB noise. And we actually modify a little bit the noise and the eyes to make it slightly smaller. So it's a form of perturbation attack. The last one, the reverse attack, which is number C, is this is a more sophisticated attack. It means that you need to find a sample that cheats the system, and then have that sample back and start seeing what exactly all the samples need to be changed to be able to do exactly the same thing. So the way it works is that you have the decision layers, and you start modifying those decision layers before making the predictions in order to have the very same sample perform as it was another sample. So this is a bit of an extensive work, but the way it works is that you have two vectors, and each vector is associated with one phase. So what you try to do is to have both vectors pointing into the same direction. And actually, it's a protection, so they give you exactly the same angle. So that's the way two samples can behave as it is exactly the same sample. So this attack is more elaborated, and actually it doesn't require to retrain the model. So it's sophisticated, and well, it was recently presented. So this is a very good attack actually. And the last attack is backdoor attack. And well, they have the same label, and what we try to do is to insert a small patch anywhere, or it could be very small, and then, well, the model activates with that patch, and they change the prediction. So actually, the model learns that when you see a patch, well, you behave differently than the rest. So you can see it here in the left, in the lower part. That's very small. So this is the patch. So we tested these attacks, and well, the pollution attack is very successful when we pollute something like 20 to 30% of the data. So after that, because you're polluting more samples, I mean, the accuracy is starting to decline, right? And the confidence starts to decline. So you will see that something is wrong. If you pollute that many samples, you will see that something is wrong. The method is not accurate, and the confidence is declining. So you may infer that something is wrong. And if you don't pollute that many samples, I mean, the model, the accuracy is very high, and well, the attack doesn't happen. So there is, I don't see, you can see the dot lines, but there is an interval where the pollution attack is more efficient. For the case of the perturbation attack, it's actually very easy to detect. I mean, you can cheat the system, but the confidence doing those predictions is very small compared with the reference confidence, which is the one you have when you train the model. So because of the confidence is very low, you can infer that something is wrong. So you can discard those predictions. So the perturbation attacks is not really an issue. So the reverse attack is severe, is the most severe. But one requirement for this is that the attacker needs to know what models, the architectural models, are making the predictions, so they can start twisting the vectors to point us to some direction. So the reverse attack is very efficient, but the attacker needs to know that what is the architecture behind the model. So the backdoor attack is also good, but the attacker needs to know the architecture of the model as well. And in that case, when the attacker knows the whole architecture, the backdoor attack is becoming more and more confident. So that's it's not having as a good penetration rate as the reverse attack. But the samples that manage to pass the system, right, they do it with more confidence. So this is also a dangerous attack when the attacker has a lot of information from the architecture of the model. So summary. Well, the proposed Bayesian model achieves competitive performance and outperforms for the case of the immediate available samples. So this is good. So compared to the state of the art, we're having better accuracy, even if we don't have that many samples. This is good. So another important outcome is that the model can be secure with up to 3-6 long key without losing accuracy. So we have keys of up to 40 elements, and without length, we still have very good accuracy. So the polynomial projection is creating a very discrete feature space that is still be able to classify. So this is one very positive outcome. And also, it doesn't require quantization. So this is very good, because normally quantization is associated with loss of information. Well, not in this case. So, well, the third part is resources pose a threat to face technology. So as I mentioned before, using existing training data or pre-processed data or even pre-trained models, I mean, you automatically are opening the door to several threats, right? So, well, this shouldn't be done. And well, the next point is the model should consider the confidence to output all predictions. So this is very important. You don't decide to this real or fake and just because of the label, right? You need to check with the reference confidence if that sample you're seeing, you are confident that you're predicting that particular label. If you're not confident, it's better not to make any predictions. So it is about practice to disclosing the model architecture. So this shouldn't be done. So you shouldn't reveal what is the architecture of the model. You have to keep it, because if you do that, you open the door for reverse attacks. So that's a very bad practice, disclosing the model architecture. So reverse and pollution attacks is posed as a real threat to the proposed system. So yes, the system is not able to. It's not robust still if the attacker knows the architecture. So the polynomial projection is not protecting the model anyways. So well, that's one of the disadvantage. So what are the conclusions and future work we're working now? So well, the efficient models, considering efficient model is a good practice to provide better accuracy, as we see, with fewer samples, and simultaneously protect against the common machine learning attacks. So this is what we conclude for this work. And improvements. Well, existing work proposed that separated models analyze coarse to fine face featuring. So they say that you can detect more accurately if you process the eyes than the nose and so on. It's right that you just create a fusion of processing the whole face. So that's something to improve. And the last bit is the immediate future work. We have to cross-evaluate different settings using more than one synthesizer. So that's another thing. So we need to combine the synthesizers and see if the model is able to detect the face, even in that conditions. So well, that's what we found out about this synthesis detection work. And well, this is it. It's your time to ask questions.
Thank you very much.